Hello and welcome to Earth Science Lecture 10, Earth's Interior. This lecture is a continuation of our earthquake discussion, and then we will also begin to look at how we know the Earth has the layered structure of its interior that we know today. About 95% of the energy released by earthquakes originates in a few relatively narrow zones located along fault surfaces where tectonic plates interact along one of three types of plate boundaries: convergent, divergent, and transform plate boundaries. The zone of greatest seismic activity, called the Circum-Pacific Belt, encompasses the coastal regions of Chile, Central America, Indonesia, Japan, and Alaska, including the Aleutian Islands. Most of the large earthquakes in the Circum-Pacific Belt occur along convergent plate boundaries, where one plate subducts beneath another at a comparatively low angle. Another major concentration of strong seismic activity, referred to as the Alpine Himalayan Belt, runs through the mountainous regions that flank the Mediterranean Sea and extends past the Himalayan mountains, which you can see in the top right of the image. Tectonic activity in this region is mainly attributed to the collision of the African plate and the Indian subcontinent with the vast Eurasian plate. These plates interact and creates many thrust and strike slip faults that remain active today. The figure shows another continuous earthquake belt that extends thousands of kilometers through the world's oceans. This zone coincides with the oceanic ridge system, a divergent plate boundary, which is an area of frequent but weak seismic activity. So we have three main areas: the Circum-Pacific Belt, where most major earthquakes occur due to our two plates moving together, so we see this in convergent zones. We have the Alpine Himalayan Belt, where we have transform and strike slip faults, which we'll learn about. And then we have the Mid-Atlantic Ridge and all the different ocean ridge systems, which also has a lot of earthquakes, but they're relatively weak. Strong earthquakes can cause major damage and loss of life, primarily because they usually strike without warning. For example, the vibration that unexpectedly shook the San Francisco area in 1989 caused 63 deaths, heavily damaged the Marina District, and caused the collapse of a double-decker section of the I-880 in Oakland, California, which you can see in the bottom right. This level of destruction was the result of an earthquake of only a moderate magnitude 6.9. Seismologists warn that other earthquakes of comparable or greater strength can be expected along the San Andreas system, which cuts a nearly 800-mile-long path through the western one-third of the United States. An obvious question then is the following: can earthquakes be predicted? Well, unfortunately, despite substantial efforts in earthquake-prone countries such as Japan, the United States, China, and Russia, no reliable method exists at present for making short-range earthquake predictions. To be useful, such a method would have to be both accurate and reliable. That is, it must have a small range of uncertainty with regard to location and timing, and it must also produce few failures or false alarms. Could you imagine the debate that would proceed in order to, let's say, evacuate a large U.S. city, such as Los Angeles or San Francisco, and the expense of doing so? Research on short-range predictions has concentrated on monitoring possible precursors, that is, events or changes that precede an earthquake and thus might provide a warning. In California, for example, seismologists monitor changes in ground elevation and variations in strain levels near active faults. Other researchers measure changes to the groundwater levels, while still others try to predict earthquakes based on an increase in the frequency of the foreshocks that precede some, but not all, earthquakes. To date, neither these nor the avenues of research have yielded a reliable method for short-range earthquake predictions. In contrast to short-range predictions, which aim to predict earthquakes within a time frame of hours or days, long-range forecasts are estimates of the likelihood that an earthquake of a certain magnitude will occur in a given place on a timescale of 30 to 100 or so years. Although long-range forecasts are not as informative as we might like, These data provide important guides for building codes so that buildings, dams, and roadways are constructed to withstand expected levels of shaking in the ground. Most long-range forecasting strategies are based on the observation that large faults often break in a cyclical manner, producing similar earthquakes at roughly similar intervals. In other words, as soon as a section of a fault ruptures, the continuing motions of earth plates begin to deform and bend the rocks until they fail or rupture once again. To determine the characteristic interval for a given fault, seismologists study the historical and geological record of earthquakes generated by that fault. A segment that has not experienced an earthquake within the past 1 to several centuries is called a seismic gap. Typically, these gaps are accumulating seismic strain and thus represent places where future large earthquakes are likely to occur. The figure on the right shows a seismic gap on the Megathrust fault that lies offshore of Padang, a low-lying Sumatran city of 800,000 people which has not ruptured since 1797. Scientists are particularly concerned about this seismic gap because rupture of an adjacent segment on the fault caused the 2004 Indian Ocean earthquake and tsunami that claimed 230,000 lives. So you can see along this megathrust fault, we saw huge earthquakes, magnitude 7.9 all the way up to a 9.2. And in the middle, there's been a gap since 1797. So this is a place where a lot of tension is probably building up and can become a problem down the road. Because P waves are less destructive and travel faster than both S waves and surface waves, they can be used to provide a type of earthquake warning system. Japan has operated such a system for over 20 years. One use of this system is to trigger automated shutdown of power generating facilities and braking of high-speed bullet trains. In addition, during the 2011 Tohoku earthquake, this system was used to send an automated alert to the nation's television stations, as well as to more than 50 million telephones. In the area closest to the epicenter of the earthquake, this alert gave residents a 10-second chance to take cover. In Tokyo, a city of around 9 million people, located about 230 miles south of the epicenter, had about 80 seconds of warning before the strong shaking began. But unfortunately, in the United States, we don't have any warning system like this in place. So this brings us to our discussion of Earth's interior. How do we know the structure and properties of Earth's deep interior? Because light does not travel through our rock, we must find other ways to see into our planet. The best way to learn about Earth's interior is to dig or drill a hole and examine it directly. Unfortunately, this is possible only at shallow depths. The deepest a drilling rig has ever penetrated is only 7.6 miles, which is about 1/500th of the way to the Earth's center. This was an extraordinary accomplishment because temperature and pressure increase rapidly with depth. Instead, much of what we know about Earth's interior comes from detailed studies of seismic waves generated by large earthquakes. About 3,000 earthquakes occur each year that are large enough, that is about 5.5 magnitude or greater, to travel all the way through Earth and be recorded by seismographs on the other side of the globe. The P and S waves from these large earthquakes can be used to see into the planet in much the same way that medical technology uses ultrasound waves to generate sonograms. Despite many recent advances, using the waves recorded on seismograms to visualize Earth's interior structure remains challenging. Seismic waves do not travel along straight paths. Instead, they are reflected, refracted, which means to change direction, and diffracted, which means to follow a curved path, as they pass through our planet. They reflect off boundaries between different layers, refract when passing from one layer to another, and diffract around some obstacles that they encounter. These different wave behaviors have been used to identify the boundaries that exist within the Earth. One of the most noticeable behaviors of seismic waves is that they follow a strongly curved path. Seismic waves also travel faster when rock is stiffer or less compressible. These properties of stiffness and compressibility can be used to interpret the composition and temperature of the rock. For instance, when rock is hotter, it becomes less stiff. Imagine a chocolate bar left out in the sun. And waves travel through it much more slowly. Waves also travel at different speeds through rocks of different compositions. Thus, the speed at which seismic waves travel can help determine the type of rocks located in Earth's interior, as well as how hot they are. So, what makes seismic waves useful for learning about Earth's interior is that, again, they do not travel in straight lines. Instead, the paths that they follow through the body of the Earth are bent because of the varying density and composition of Earth's interior. By studying how the paths of these waves bend, geologists can map out the general interior structure of the Earth. One key observation about seismic waves and how they bend has to do with the difference between S and P waves. When an earthquake occurs, seismometers relatively close to the epicenter will record both S and P waves, which you can see up at the top anywhere in this orange region. You can see both S and P waves with detectors in that region. When an earthquake occurs, seismometers relatively close will again record both S and P waves, but seismometers on the opposite side of the Earth, down here, only record P waves. Transverse vibrations, such as S waves, cannot travel far through liquids. So it was therefore concluded that our planet had a liquid core. So something stopped S waves from getting to the other side of the Earth. So because liquids stop our S waves, we conclude that there is a liquid portion inside the Earth. There is also a region in which neither S nor P waves from a distant earthquake can be detected, as you can see in this blue area. This, quote, shadow zone results from the way in which P waves are deflected at the boundary between solid mantle and molten core. By measuring the size of this zone, geologists have concluded that the radius of the molten core is about 55% of our planet's overall radius. Some of the P waves passing through the Earth are deflected into the shadow zone by a small, solid inner core at the center of our planet. So, the properties of Earth's layers include the physical states of the materials, that is, solid, liquid, or gas, as well as how strong the material is. For example, the distinction between the strong lithosphere and weak asthenosphere. Studies have shown that Earth's layers are mainly caused by differences in density, with the heaviest and densest materials, such as iron, at the center, and the lightest ones, such as gases and liquids, toward the outside. So this is mostly a slide for reference. It shows a cutout of the Earth. So we see the inner core, outer core, and mantle, and then a zoom in of the section near the surface, where we see the crust, lithosphere, and the asthenosphere. So this is a great reference for any student working on problems. Let's step through each layer with a little bit of detail, starting from the top and working toward the center. The crust is Earth's relatively thin, rocky outer skin. The two types of crust, continental and oceanic, have very different compositions, histories, and ages. In fact, oceanic crust is compositionally more similar to Earth's mantle than it is to the crust of the continents. Earth's oceanic crust, which forms along mid-Atlantic ridges, as we talked about previously, mid-ocean ridges, it doesn't have to be in the Atlantic, is about 4 miles thick. The rocks of the oceanic crust are also younger, as we discussed, about 180 million years in age or less. They are also more dense than continental rock. Ocean crust has density of about 3 to 33 grams per cubic centimeter, of about 3 grams per cubic centimeter, and is composed of the dark igneous rock basalt and gabbro. Unlike oceanic crust, which has a relatively homogeneous chemical composition, continental crust consists of many rock types. Although the upper crust has an average composition of granitic rock called grandirite, its composition and structure vary considerably from place to place. Continental crust averages about 25 miles thick, but can be more than 40 miles thick in the mountainous regions. It has an average density of about 2.7 grams per cubic centimeter, so slightly less dense than the ocean crust. So, as a result, the low density of the continents relative to the mantle explains why continents are buoyant, acting like giant rafts floating atop the mantle, and why they cannot readily be subducted like our oceanic plates. The discovery of continental rocks, more than 4 billion years old, provides evidence that continental rocks cannot be easily recycled into the mantle. Speaking of the mantle, more than 82% of Earth's volume is contained within the mantle, which is a solid, rocky shell that extends to a depth of about 1,800 miles beneath Earth's crust. The boundary between the crust and the mantle represents a marked change in chemical composition. The dominant rock type in the uppermost mantle is periodite, which is richer in the metals than the rocks found in either of the crusts. The upper mantle extends from the crust-mantle boundary down to a depth of about 410 miles. Recall that the upper mantle is divided into two different parts. The top portion of the upper mantle, along with Earth's crust, make up the stiff lithosphere. The lower unit of the upper mantle contains the weak asthenosphere. The lithosphere, or sphere of rock, forms Earth's relatively cool, rigid outer shell that is broken into sections of various size called tectonic plates. The lithosphere is more than 155 miles thick below the oldest portion of the continents and about 60 miles thick below the seafloor. Beneath Earth's lithosphere is a solid but comparatively weak layer termed the asthenosphere. Because the asthenosphere and lithosphere are mechanically detached from each other, the lithosphere is able to move independently of the asthenosphere, which allows for plate tectonics. From 410 miles deep to the top of the core, at a depth of about 1,800 miles, is the lower mantle. Because the pressure in the mantle increases with depth due to the weight of the overlying rock, the mantle becomes stronger with depth. Despite their strength, the rocks in the lower mantle are extremely hot, and as a result, they are capable of very gradual flow. Okay. The core is thought to consist mainly of iron, combined with an unknown quantity of nickel, as well as a minor amount of oxygen, silicon, and sulfur, elements that readily form compounds with iron. Because the extreme pressure found in the core, this iron-rich material has an average density more than 10 times the density of water, or about 10 grams per cubic centimeter. The outer core is a liquid, iron-rich layer 1,410 miles thick. The liquid nature of the outer core was discovered when researchers found that S-waves do not penetrate the outer core. Scientists concluded again that because S-waves do not travel through liquids, that the S-waves allowed us to find out that the Earth's core must be liquid. At Earth's center lies the inner core, a solid, dense metallic sphere with a radius of about 754 miles. Despite its higher temperature, the inner core is solid, not molten like the outer core, due to the immense pressures that exist at the center of our planet. The density at Earth's center is about 13 times that of water, or 13 grams per cubic centimeter. If we could slice Earth in half, the first thing we would notice is that it has distinct layers. The heaviest materials, or metals, are in the center, with less dense solid rock in the middle, and lighter liquids, mainly water and gases, at the top. Within Earth, we know these layers as the iron-rich core, the rocky mantle and crust, the liquid ocean, and the gaseous atmosphere. There are also variations in Earth's composition and temperature with depth, which indicate that the interior of our planet is very dynamic. The rocks of the mantle and crust are in constant, if very slow, motion. In addition to the plate tectonics, these motions cause continuous recycling between the surface and the deep interior. Furthermore, it is from the Earth's deep interior that the water and air of our oceans and atmosphere are replenished, allowing life to exist at the surface. According to the nebular theory, Earth and the solar system began to form nearly 5 billion years ago due to the gravitational collapse of a huge cloud of dust and gas called a nebula. As material accumulated to form Earth, and for a short period afterward, the high velocity impact of debris and the decay of radioactive elements caused the temperature of our planet to increase steadily. During this time of intense heating, Earth became hot enough to melt iron and nickel. Melting produced dense blobs of liquid metal that sank to the center of the planet. This process occurred rapidly on the scale of geological time and produced Earth's dense iron core. The early period of heating resulted in another process called chemical differentiation, whereby melting formed buoyant masses of molten rock that rose toward Earth's surface and solidified to produce the primitive crust. These rocky materials were rich in oxygen elements, particularly silicon and aluminum, along with lesser amounts of calcium, sodium, potassium, iron, and magnesium. In addition, some heavy metals such as gold, lead, and uranium, which have low melting points or were highly soluble in the ascending molten material, were scavenged from Earth's interior and concentrated in the crust. This early period of chemical differentiation established the three basic divisions of Earth's interior: the crust, the core, and the largest layer known as the mantle. So there's a lot to take in here, but this is basically saying that Earth started as a giant molten ball of rock. The densest stuff sank to the center, whereas the less dense material rose to the top. And that's why we have a layered structure to the planet. So last but not least, I just wanted to include a graph of temperature and the melting point of different rocks throughout the depth of our planet. So both temperature and pressure increase with depth below the surface. The crust is composed of rocks for which the melting point is far higher than the actual temperatures. So as a result, they don't melt, and so we have a solid crust. Materials in the asthenosphere, which is that semi-fluid layer, have a melting point just low enough for melting to occur, which is why materials can flow in this region. So right here, we see the actual temperature in yellow is just slightly above the melting point of the rocks in that layer. So it's semi-molten. We then get to the mantle, where we see the temperature is well below the actual melting curve of rock, so it's solid again. But because of the differences in composition, when we get to the outer core, suddenly we jump up and have a molten region again, before coming back down to the core where it's so dense that it becomes solid once more. So this temperature curve just helps to explain why we have the differences in physical properties at different layers in the Earth. So as usual, let us conclude our discussion of earthquakes with a few questions. So read the question, pause the video, and when you think you have an answer, return. Number 1. When an earthquake occurs, energy radiates in all directions from its source. What is another name for the source? All right, in this case, you have to be careful. It's the focus. This is the location where slippage begins, and it's called the hypocenter or focus. A lot of students I've found choose epicenter because that's what they typically hear when talking about earthquakes, but epicenter just happens to be the point above the focus, so it's the point on the surface where the earthquake occurred. Number 2. Which seismic waves arrive first at a seismograph station? Okay. The fastest waves and those that arrive first are P waves. These are the first waves to arrive at a seismic station, then followed by S and surface waves. For me, one way to remember this is P stands for primary, so I think primary being first. Question 3. On a typical seismogram, blank will show the highest amplitudes. In other words, where do we see the strongest waves at the surface? Okay, in this case, it is C, surface waves. Surface waves have the highest amplitudes on a typical seismogram. So in this case, P and S waves, although they travel faster, they are weaker than the surface waves. And last but not least, number 4. On the Richter scale, a magnitude 6 earthquake causes about blank times more ground shaking than magnitude 4. So it's 2 magnitudes higher. So what does that mean about its shaking? Okay, well remember it's a logarithmic scale, which means it increases at an increasing rate. So basically, for every step up in magnitude, we have an increase in about 10 of ground shaking. So if we jump up twice, we're jumping up by 10 times 10, which is 100. So we see a 100-fold increase in amplitude. Okay, so that's it for our earthquake discussion. From here, we're going to move on to volcanoes and other processes that are working at the surface. Thanks for watching, and have a great day.